There's another subspace called the column space of a matrix A. The definition of a column space, we're going to denote this as col A, is the set of all linear combinations of the columns of A. Now, if we let A be given by this many columns, then you can see clearly that the column space of A is just equal to the span of the columns of this matrix, just by definition. Span is the set of all linear combinations, so that's the definition of column space. If your matrix is an m by n matrix, yes, there are n columns, but each one of those columns has to live in Rm. And so that means that the column space of A is a subset of Rm. As you're going to see by the name, column space of A is a subspace of Rm because it's a span. Remember earlier we said that anytime you have a span, it's automatically a subspace. Well, a column space is automatically going to be a subspace. It contains the zero vector. You can take none of each of the columns. If you take any linear combination of the columns, it's still in the column space by definition. Doing things with the column space, you are asking about linear combinations of the columns. So if I give you this example from earlier, I would now like to know whether or not this vector is in the column space of the matrix. Asking that question is like asking, can W be written as a linear combination of the columns of A? And another way of saying that is, can I find some C1, C2, C3 so that W is C1, A1, where this is A1, C2, A2, where this is A2, and C3, A3, where this is A3. And that means you have to solve AX equals W. And solving AX equals W is now just a row reduction problem where you're going to take that system, but you're going to augment it now with W on that side. And so you can go ahead and do the row reduction, and what you're going to find is that you will end up with something that looks like this. And you can see this system will have a solution. There are actually going to be many solutions. W is therefore a linear combination of the columns of A. Therefore, W is in the column space of A. So in the problem, we had a 3 by 5 matrix. The column space of A is going to be some sort of subspace of R3 because each column has 3 entries. By definition, the column space of A is going to be the span of all 5 of those columns. But I would love now to know a basis for the column space of A. We need to figure out which of the columns are linearly independent. That has to do with putting things into a row-reduced echelon form. Our matrix A could be row-reduced to some new matrix. I'm going to call it B. That looks like this. We are interested in the number of pivot columns. So there are 2 pivot columns and 3 free variables. The pivot columns are linearly independent. So if I were to just take those 2 columns and put them into a matrix, the only way to make these 2 columns add up to 0 would be trivially. If I were to say this is B1 and this is B2, C1B1 plus C2B2 can only be 0 if C1 and C2 are 0. If I put a weight in front of this, the only way to make that up to 0 is by putting this weight to 0, and the only way to make this entry 0 is by putting this weight to 0. You have to be a little bit careful. When we talk about the basis for the column space of A, we are legitimately interested in the matrix A, not in its row-reduced equivalent. Row operations preserve solution sets. If C1 plus B1 plus C2 B2 equals 0 has a solution C1 C2 equals 0 0, that means because A and B are row equivalent, C1 A1 C2 A2 equals 0 only for the same answers. It preserves the same solution set. C1, C2 is 0, 0. The first 2 columns of A are also linearly independent. When you row reduce, you preserve solution sets. So that means any vectors that are linearly independent in the reduced form must also correspond to linearly independent columns in the original. So a basis for the column space of A is just the pivot columns of A, the set A1 and A2, and that means that column space A has a dimension of 2, which is just the rank of the matrix. Column space A is a plane in R3. These 5 columns of the matrix A form a plane. You don't need those 5 vectors. Only 2 of them have pivots. 3 of the vectors are just dependent on the other ones. Be very careful. Don't use the columns of B, the reduced form, for the basis of the column space of A. When you reduce a matrix, when you'd have a matrix, let's say like this, 1, 3, 2, 6, and you reduce it to something like this, 1, 3, 0, 0. Yeah, there's a pivot here, which means this is the only independent one, which means this is the only independent one. But the span of that vector is a line along the x-axis, whereas the span of this vector is not. So make sure you're using the right one. Finding the basis of the column space is easy. You take your system, you row reduce it, and you find the pivot columns. Take the columns that correspond to those from your original matrix A, and you've got it.